Welcome to Measure Theory. This is the 18th session. Today we are going to start on Lebesgue integral of a measurable function. But the first step is to define the Lebesgue integral of a simple non-negative function. Okay, so let us get started. So recall that if f is a step function, so that means I have various points, right? And here, this is a constant, okay? And this will be this constant. I may not be drawing correctly, but you understand what this means. This maybe is like this. Okay, assume these are non-negative. Okay. Then the area under the graph, okay, as I said, the picture is not good, but you understand what I mean. Okay. And suppose this is C1, C2, C3, C4, and C5. These are the partition intervals are J1, J2, J3, J4, and J5. Then, okay, the area under the graph. This is what we usually mean. This means the area of the region or the set enclosed by, let us say this is equal to A, this is equal to B, enclosed by X equal to A, X equal to B, and Y equal to 0, and Y equal to F. Okay, this is Y equal to F. Okay. So, is nothing other than Ci into length of J. I equal to whatever 1 to n. Here I just put only n equal to 4, 5, but you know what it means, right? This is what we want to generalize. So, let X be mu be a measure space. Okay. Let F equal to summation Ci indicator function of I equal to 1 to n be a simple function, simple non-negative function in its standard representation. So what does that mean? This means my X is a disjoint union of I equal to 1 to n, let us say this disjoint. That's a partition, right? The A's are pairwise disjoint and measurable. And I am assuming Ci's are positive here, right? Then we define the integral. The notation is f x du mu by setting integral f x du mu equal to summation Ci mu of I equal to 1 to n. Right? So think of the picture, have some kind of an idea. Okay, so for I have this may be some partitions. On each of them there is this is my C1, this may be my C2, this may be my C3, this may be C4. So when I want the volume, what do? The area of this region into the height. That's what we are doing. Okay, so exactly similar thing is what we are doing. Okay. And notice that there is a possibility that one of the, and remember we always assume my Fi's are my simple functions take values only in R. Okay, so now the infinite value is not assumed. Okay, right. Is this clear? Let us look at a very first example. Therefore, if my f is characteristic function of a measurable set E, so what is integral of f d mu over x? This is by definition, you can see this is, therefore f is this one, therefore it's going to be 1 times measure of E, which is measure of E. Okay, this is the first example, very trivial example, right? The second example is, let us look at my thing f to be characteristic functions of q intersection 0, 1. Right? Notice that this is an analog of Dirchlet's function. Dirchlet's function was from 0, 1 to r, and which is nothing other than the characteristic function of q intersection 0, 1. The domain is 0, 1, therefore 0, right? And you know that this is not Riemann integrable. But here you can see q intersection 0, 1 is a measurable set. So I should have said what is the measure space. The measure space is R with the Lebesgue measure. Okay, this is our measure space. Right? Now q intersection 0, 1 is a measurable set. Right? And we know it's a measure, namely m of this, call this parameter A or E. Okay, m of E is 0. Therefore, by 1, we find that integral of f dm over r is 0. Okay, now my m is, the mu is m, x is r, therefore I am writing this. Right? In particular, you can see that we can talk about the integral of Dirchlet's function. Okay, the very first, more or less the first example itself, okay, shows that I have lot more, at least one function which is not Riemann integral, is Lebesgue integral. Okay, it has the meaning of. So I went ahead as usual 10 minutes without sharing the screen, so I have to re-record. Okay, so for notation reasons, okay, we have one kind of give a different notation for Lebesgue integral also. We will show that. So let us assume that x is again x p mu to 0 and infinity. Okay, this is a positive symbol. Okay, and this is the integral or x. Sometimes one also writes this as, because in Riemann integral on calculus we wrote integral a to b f of x dx, right? Therefore, sometime to make sure that we are talking about the variable and do that. Okay, this is same as this. Okay, and if mu is clear, if x is clear, then we may even write integral of f d mu. And if everything is fixed, then I may even write integral of f without saying over x and over with respect to the measure mu. Okay, so this is called the Lebesgue integral of f with respect to the measure mu. The moment you say measure, then the sigma algebra is already determined. Okay, and there is another reason why we want to do. Suppose f is a function from x, the mu to again 0 infinity. Let it be simple, okay. Then if we may want to define integral of f over e, not on all of x. Okay, the way we define is the following. It's something like, suppose f is a function from r to r, and suppose I have an interval a b, then I can define integral of a to b f of x dx, right? Even though the function is originally defined on all of r. Okay. Similarly, f may be defined on all of r x, but I want to define integral of f over e d mu. This by definition is integral of f into indicator function of e into d mu over x. Okay. So what does this mean? Right? Notice that indicator function of this okay at x equal to fx into indicator function of e at x. This is equal to fx if x is in e and 0 if x is not in e. So it is same as saying I am extending. Okay, this is clear? Yeah. So and this is measurable. This is measurable. Therefore, this is measurable. The next thing is why it is simple. Yes, is this simple? Because we define integration of only single non-negative function. So this is certainly non-negative. Is it simple? Okay. Now suppose that is also clear because of my fi is, let us say, ci indicator function of ai. Okay. And I equal to 1 to n, and this is standard representation. Okay. So I want to know what is this is it simple? Okay. Before doing that, let us look at two things. Suppose my indicator function is indicator function of a, another thing is indicator function of b. I want to know what is f times g. F times g at x is exactly as we did earlier. If fx into gx, which is indicator function of ax into indicator function of bx, which is equal to 1 if x is in a and b, and 0 otherwise. Right? If it has to be there in both, otherwise it has to be 0. Is that clear? Therefore, this fellow is nothing other than indicator function. That is indicator function of a into indicator function of b is indicator function of a intersection b. So pause, review, proceed. Now let's come back. So f is already a simple function. Ci indicator function of I equal to 1 to n. My g is indicator function of a measurable set. Now I want to know what is f times g. Notice that it is certainly a measurable function, and since we are assuming this is positive also, okay, this is measurable and non-negative. So only question is the values. Okay, but you can even say something more. Notice that. Okay, let us look at. Therefore, f into g is nothing other than ci into I of ai into I of v, I equal to 1 to n. Therefore, this is nothing other than ci intersection ai intersection e, I equal to 1 to n. Right? And certainly this is simple. Not only it is simple, yeah, okay, this is a standard representation. Okay, right. So therefore, what is integral of f or e? Then this by definition therefore is integral of f into indicator function of e over x. But this we already know, this is nothing other than summation ci indicator function of a of e. Okay, this is the simple function, therefore its integral is ci into mu of a intersection e, I equal to 1. Therefore, we have found the formula if f d mu over x is summation ci mu of a, but f integral of f over e with respect to mu is ci mu of a intersection. Okay, pause, review, proceed. We already did some integrate or intersection. Let us look at two measurable sets A and B in B now. Right? Then let's look at A, I, and B. Right? So if my E is this, okay, therefore what is the integral integrator function E? This we saw its measure of A union B. Right? But on the other hand, this, okay, I may be able to write in a slightly different way as we have done earlier. Right? How did you do that? This may be my A, this may be my B, and this is my A intersection B. Okay, this is A intersection B. It doesn't look nice, that color, right? Okay, this is A intersection B. And therefore this is A minus B. And this is B minus A. Therefore my E, which is A union B, I can write it as A minus B union A intersection B union B minus A. Right? And this is a pairwise disjoint union. Therefore, IE of B is nothing other than IE of A minus B, integrated function of A intersection B, plus integrated function of B minus A. Correct? Yeah. So, now the simple function, call this as a simple function F. This simple function F, now I wrote it not necessarily this way. I of A minus B plus I of B minus A plus I of A intersection B. This is not a standard representation. Why this is not a standard representation? Because the F takes only 0 and 1. Okay, therefore what should I do? My C1, it is C0 is 0, C1 equal to 1, then it should be, okay, then my C1, the value is taken over A union B. This is taken in A union B complement. Therefore my F is actually 0 times integrated function of A union B complement plus 1 times integrated function of A union B. You understand? This is a simple representation. Okay, but I got this. This is the, sorry, this is a standard representation of this simple function. But this is non-standard. But we already know, okay, integral of 1i A minus B, etc. This is mu of A minus B, and similarly mu of B minus A and mu of A intersection B. And we also know they add up to mu of A union B. Why? That is because finite additivity. A union B is A minus B union B minus A union A intersection B. Okay, pairwise disjoint measurable sets. Right? Therefore, mu of this equal to mu of this plus mu of this plus mu of this. Right? And are you following? Therefore, if the same function F, which is I of A union B, I wrote it as A minus B plus B minus A plus I A intersection B. Okay. Then I found this integral is also the same. Okay, this is equal to, then integral of F is also equal to, okay, this. So what I want to say is the following. Yeah. So please pause, review, proceed. So this example shows sometimes a simple function is expressed as a linear combination of pairwise disjoint linear combination of pairwise disjoint indicator functions are pairwise disjoint measurable set. That is my a simple function standard representation exists, but it may be equal to ci times indicator function of ei. Ei's are pairwise disjoint, but this representation sigma ci indicator function of ei need not be the standard representation of the simple function. Right? Please look at this case. But we want to say even in that case, I know how to compute the integral. If I didn't get the standard representation, I had another representation, but I can still compute the integral of the simple function. Please understand? Okay, I'll explain that. We will formulate as a trivial lemma, very crucial. We will do that. So this is a very technical, easy lemma here. Technical and crucial. It's not R, and simple lemma. What does it say is, let f from x be mu to 0 infinity be simple. Let f equal to, let us say, beta I, beta j in bj, j equal to 1 to n. Maybe first I'll write. Let f equal to summation alpha I, f I equal to 1 to m be the standard representation. Assume that, okay, f is also equal to beta j I of indicator function bj, j equal to 1 to n, where of course my bj's are measurable and pairwise disjoint. Then what you want to claim is, then integral of f d mu over f is nothing other than beta j into mu of bj, j equal to 1 to n. You see that? That's exactly what we did. I had I of a union b, indicator function of a union b. I wrote it as indicator function of these three objects, and these are pairwise disjoint. Therefore, I found integral of f d mu is nothing other than c1 times, that is c1 is in this case 1 times measure of this plus measure of this plus measure of this. Okay, please understand. So what is the important assumption? The important assumption is these beta j's are mutually pairwise disjoint. That's the important thing. It's not for anything. Do they occur naturally? We are going to see. Okay. We already saw A union B, and exactly that's the case where it is going to occur. We will see it later. Okay. Now how will I do that? First notice that, see, fx is summation alpha I indicator function of I equal to 1 to n. This is also equal to beta j I indicator function of beta j equal to 1 to n. Right? Therefore, the values alpha I equal to 1 to m is exactly the values beta j equal to 1 to m. So, notice that here we used, okay, bj's are mutually disjoint. Because what are the possible values? Let x belong to x, then fx will be summation beta j and I bj of x. Therefore, only one, since these are our, okay, pairwise disjoint, okay, therefore my x will belong to exactly one of them. You understand that? We are assuming, as usual, my A is from a measurable partition, which is for a measurable partition. Therefore, x has to be in only one of the j. Okay? Right. Please understand. Alright? So, this will be beta j if x belong to bj. Right? Therefore, they are the same. Therefore, what I can do is, say this is a standard representation. Okay, so it makes sense to collect my beta j's out to be alpha i's in some order. You understand that? Therefore, for each I between 1 and n, 1 and m, okay, let us put ji equal to set of j so that my j equal to my beta j equal to alpha I. Again, have a picture. A picture may help you. So this is my this is my way. Okay, this may be my a's. My betas may be like this. Okay, b1, and this may be my b2. This may be my b3, and b4, b5, or maybe called b5, b6, or maybe, okay. Then what does it mean? My all beta 1 equal to beta 4 equal to alpha 1, and so on. Yeah, whereas here beta 3 and beta 5, this is 5, beta 5 equal to alpha 3, and so on. Do you understand that? Right? And the second thing I want to notice also, what is my A? A I claim is nothing other than Bj, J running over J running over Ji. Is that clear? Why? If x belongs to Ai, what does it mean? If only if x is alpha I, right? Now this x belongs to alpha I, but alpha I, right? Now where does x belong? If x belongs to this union, that means there is a j in Ji, so that fx belongs to bj. But then fx equal to alpha I. You understand that? Yeah, pause, review, proceed. Therefore, my mu of A is nothing other than summation mu of bj, j running over ji. And these are, remember, these are pairwise disjoint, therefore by finite additivity. Right? Okay, now let's do this. Therefore, integral of f d mu over x by definition is summation alpha I mu of I, right? And the other one, let us look at this, beta j into mu of bj, j equal to 1 to n. Okay. Now this I split into, since j is union of ji, this is also disjoint, pairwise disjoint union. Therefore, this 1 to n, I can write it as j1 union j2 union jm, right? Are you following? Therefore, that is going to be I equal to 1 to m of j running over ji is into beta j into mu of bj. But that is I equal to 1 to m. This, but when j belongs to ji, this is nothing other than alpha I. Alpha I is common to all of this, therefore I can take alpha I and then take mu of bj. And this j running over ji. But we saw this. This is nothing other than mu of I. Therefore, this is equal to alpha I mu of I equal to 1 to m. That is integral of FD. See that this kind of things are never easily checked. It's all very easy. They leave it. I took pains to explain because you should feel confident, and also it makes you understand what are the things which are involved. So This is a very important result, very easy technical result, but it's very important. Okay. So we are now going to list some of the properties of the integral of a simple non-negative function, and in one of them this lemma will be used also. Okay. I do not know, I may be running out of time because there was some long gap. Somebody was talking on the phone. So let me just quickly state the result, continue in the next session. So this is the theorem. Let X be mu be a measure space. Let S plus equal to set of simple functions, set of simple non-negative functions on X. Remember, all my simple functions are measurable. Then the integral, okay, from S plus to 0 infinity going to F, going to integral of F d mu has the following property. The first one is easy one. If C is positive, F is S plus, then C F belong to S plus. This is very easy. And integral of C F d mu over X is C times integral of F d mu over X. Okay. Second thing, if F and G are in S plus, then F plus G also is in S plus, and integral is additive at least here. F plus G d mu over X is integral of F over d mu plus integral of G over d mu. Okay. And third thing is, if F and G are in S plus and F is less than or equal to G, then monotonicity integral of F d mu is less than or equal to integral of G d mu. And fourth one is something very fantastic. It's a countable additivity. What does that mean? If En's, okay, a pairwise disjoint family, N of B, let E equal to union En, then let F be a simple function, then integral of F over E d mu equal to summation integral of F over En d mu. Right? So notice that, what does this mean? This is something, this is my, call it E, and E is a union of various pairwise disjoint thing. Okay, then integral F, I evaluate, okay, or evaluate integral F for all of E, then they all add up. Okay, so as I said, I may not have time, so I will just, this is very easy. C is greater than 0. Suppose F, this is a single thing, Ci times identity of Ai, I equal to 1 to N is the standard representation. Then C times F is C times Ci times Iei. This is the standard representation, and CCI is positive for all I, non-negative. Okay. And second thing, this is the very interesting thing. Suppose F equal to, let us say, alpha I of Ai, I equal to 1 to N. Standard representation. G equal to beta j, indicator function of Bj, j equal to 1 to N. This is also standard representation. Then F plus G, okay, this is a symbol, and assume these are all in S plus, then this will also be in symbol. Because as you had already observed, if F and G are simple, F plus G is simple. This we already observed. Whether negative, non-negative, anything. Okay. We had already observed this simple. And the possible values are alpha I plus beta j, where 1 less than or equal to im, 1 less than or equal to j less than or equal to n. Okay, possible values, not all values may be taken. Okay, all these things we had already seen. Now the interesting thing is, what I do not know is I may not find the standard representation. Able to find the standard representation of f plus g. But let us look at this. F plus g, I can write it as in terms of, okay, I can write it as summation, let us say gamma r, okay, and something. Let me write it in a slightly different way. I can write it as a linear combination of integrated functions of pairwise disjoint measurable sets. Suppose, let us not worry about what it is. Suppose I write it as CR I equal to 1 to n. My f plus g is this. ERs are pairwise disjoint. Then I know integral f plus g, we had already seen this is nothing other than CR times mu of VR. Okay, this is by lemma. Right? So somehow I have to find this. How will I find this? That is because notice that by always our assumption is bj running from 1 to n is x. This is a partition, and similarly I running from 1 to m. This is a measurable partition of x. Right? Therefore my ai is going to be ai intersection bj, j running from 1 to n. And similarly bj is summation, union bj intersection ai, I running from 1 to m. And these are all measurable partitions. Right? So I want to say f plus g of x is equal to, I want to write it in terms of these things. Okay? Please think over it. We will do it in the next session because it's already exceeding time. Okay, but I already pointed out why that lemma is important. Alright, this is very easy. What you do is a intersection bj as I and j vary, that is a partition. Do you understand that? This is a double indexed family, a intersection bj, I and j vary. This is a measurable partition. Maybe there are some limits are empty. Okay, this is a measurable partition of x. Therefore, I want to write f plus g as linear combination of integrated functions of this. Think about it. How will it happen? If x belongs to a intersection bj, then fx must be equal to alpha I. But x belongs to bj, it must be beta j. Therefore, I can write f plus g equal to summation alpha I plus beta j into integrated function of a intersection bj. Think about. So there is still some time. So let me continue. Because of interruptions, I thought actually after I started the lecture about 70 minutes is over, but then due to interruptions, okay, there is still time. So let us get. So therefore, if I have, as I said, if x is union of a intersection bj, I and j both vary, this is a pairwise disjoint union. Right? Therefore, if x belongs to capital X, there exists a unique pair I and j such that x belongs to ai intersection bj. Right? So if x belongs to a intersection bj, then what is f of x? F of x is going to be, since x belongs to ai, f plus g at x equal to f of x plus g of x Since x belongs to a, f of x will be alpha I. Since x belongs to bj, it will be beta j. Therefore, it is this. Right? Therefore, f plus g equals summation alpha I plus beta j into integrator function of a intersection bj, I and j running. I running from 1 to m, j running from 1 to m. Okay. Therefore, by lemma, integral of f plus g d mu x equal to summation alpha I plus beta j into measure of a intersection bj, I equal to I and j. Okay, I equal to 1 to m and j equal to 1 to n. Right. Now let us try to reformulate. This is, let me take alpha I into mu of a plus a intersection bj, and let me run this over g, a intersection. Okay, are you following? And then this is our I. Plus similar thing I do with j. J, I take beta j and sum it over I of alpha I, sorry, mu of a intersection bj. Okay. See, this alpha I comes out, therefore this summation alpha I over I and summation of this mu of a intersection bj, j, but this is nothing other than mu of a. Similarly, this is summation over beta j, this is summation over I, and j is held fixed. Since union a equal to all of x, this will be bj. We already saw that, right? But this is nothing other than integral of g over d mu. This is nothing other than integral of f d mu. So we have shown that, therefore we have shown that integral of f plus g d mu over x is integral of f over d mu plus integral of g over d mu, where f and g are positive simple functions. Okay, pause, review, proceed. The third point, monotonicity, is exactly similar. If f and g are in S plus, f is less than or equal to g, then integral f d mu is less than or equal to integral g d mu. So keep the notations above. Two. Okay. Then let us look at, if x belongs to, so I know x is union of a intersection bj, right, where I and j. If x belongs to a intersection bj, notice that it may be empty. In that case, there is no problem. Okay. Then let us look at what will be my fx. If x belongs to a, it is going to be alpha I, and since x belongs to bj, okay, therefore gf is beta j, right? But fx is less than or equal to gx for all x implies alpha is less than or equal to beta g. Do you understand that? Therefore, if whenever x belongs to a intersection bj, then alpha is less than or equal to beta j. Now we are ready to write the proof. Now what is f? F is equal to summation alpha I of ai. But remember, my ai is union of a intersection bj over j equal to 1 to n. Therefore, this is nothing then. Again, it's a pairwise disjoint. Therefore, I of ai equal to I of summation I of a intersection bj. Therefore, alpha I summation over I equal to 1 to m, and this is j equal to 1 to n I of a intersection bj. Right? Are you following? But what we know is this is less than or equal to summation beta j intersection I equal to 1 to n. Yeah, okay, keep this clear. Therefore, what I have now, Therefore, integral of f by definition is equal to alpha I mu of a intersection bj, this summation over j, summation over I. But this is less than equal to I. Okay, so on this my beta alpha I is less than equal to beta j into mu of a intersection bj. Right? Now interchange the summation, that is going to be beta j, this is over j first, into I mu of a intersection bj. But this is equal to summation bj into mu of bj, which is integral of g. Therefore, integral of f is less than equal to integral of g. Please don't feel intimidated. The ideas are very simple. Okay, keep the ideas in mind. Okay, very simple set theoretic results are what is needed. Okay, and many times so one writes it and then you follow. Okay, you do it on your own. Now let's prove the last result. Last result is En pairwise disjoint family in B and E is union AI. Then we want to prove, and F is a simple function, then we want to prove F over E is summation F over En. Remember, as I said, these are all understood. Okay, so let us assume my F is summation alpha I of I. Now I equal to 1 to m. Since I am using n as a running index, I don't want to use that. Okay, this is a standard representation. Yeah, right? Therefore, integral of f, and notice that my ai equal to union of ai intersection k equal to or n equal to 1 to infinity. Oh, you know, A intersection E is what I want. So let me just say, sorry, A intersection E is union A intersection n equal to 1 to infinity. Correct? Now, integral of f over E by definition is summation alpha I mu of A intersection E. Right? Now, this is a pairwise disjoint collection and all are measurable. Therefore, by countable additivity, mu of A intersection E is nothing other than summation mu of A intersection n equal to 1 to infinity. Therefore, this fellow is nothing other than alpha I equal to 1 to m and then summation over n of mu of A intersection n. N is 1 to infinity. Okay. Is this clear? Pause, review, proceed. Now comes a simple fact. Okay. An observation in that from infinite series. Theory of infinite series. What is it? Suppose, let us assume my summation akn, okay, n equal to 1 to infinity, akn's are all positive, okay, and k running from 1 to m. So there are 1 to m. There are k in infinite series of non-negative terms. Right? Now there are two things I can form. I can form this one, a1n plus a2n plus amn, and therefore n is running from infinity. This is one single infinite series. I also have this one, summation a1n 1 to infinity plus summation a2n 1 to infinity plus summation am n equal to 1 to infinity. Okay, this shortened notation will be k equal to 1 to m of a k n equal to 1 to infinity, and this is shortened notation will be n equal to 1 to infinity, and this summation will be k equal to 1 to m of a k n. Okay, pause. You understand? Make sure that you understand. No, notation not be. So it's simple. What I'm saying is summation an, summation bn, and summation an plus bn. Right? What you want to say is summation an plus bn equal to summation an plus summation bn. You may say this follows from the theory of infinite series. Remember, you proved it under the assumption these are all convergent series. If this is a convergent series, then this is also convergent, and this sum is equal to this. Are you following? But our thing is not convergent. It may or may not converge. So but then the result is the same. If a non-negative, we want to say, okay, k equal to 1 to m of a k n equal to 1 to infinity is same as summation k equal to 1 to m of a k n equal to 1 to infinity. You should understand what you are doing. Please understand. This means this is the sum. A. Okay. This is the question. Right? Now, the way to do, you have to prove this by looking at the partial sums. Okay. What is the partial sum of this? Partial sum of this is going to be k is 1 to n, right? That's the written. Then only n has to vary. Therefore, it is a11 plus a m1, a the next will be a21 plus a, well, let me see, k is, I am running from k. It will be easier if I look at this way. Yeah, k is running from 1 to n, therefore it will be am1. Next will be k equal to 1 to am2, and next will be a1n plus amn, right? Are you following? But this I can add this as partial sums here. This is a finite sum, right? Therefore I can add this way, a11, a12 plus a1m plus dot am1 plus amn. Okay, that's the partial sum of this series, right? So letting n tend to infinity, if you find this little more confusing, stick to only 2. Okay, it's important to understand the case. After that, general case will follow easily. Okay, for example, suppose I have an plus bn, and here I have summation an plus summation bn, right? The partial sums, let us call it un, the partial sums is sn and tn, right? Then what is un? Un is a1 b1 etc plus an bn, but that's nothing other than, because the finite sum, I can group them separately, right? But this is nothing other than partial summation, partial sum tn. Therefore, okay, limit of un is limit of sn plus limit of tn. This may not converge, but remember, these are all increasing. Sn, tn, un are all increasing sequence of non-negative terms, numbers. Okay, therefore the result follows. I forgot to share as usual. Okay, suppose I have summation this, called the partial sums as un, partial sums of this is Sn and Tn, then what is Un? A1 plus B1, etc. An plus Bn. But since it's a finite sum, I can group only these fellows. A1 to An plus B1 to Bn. But that is Sn plus Tn. Therefore, my Un is Sn equal to Sn plus Tn. And remember, Sn, Tn, Un are all non-negative. Okay, they are also increase, right? Therefore, well, limit of this is the supremum of Un, the supremum of Sn, supremum of Tn. LUB of Un will be equal to LUB of Sn plus LUB of Tn. But that is the summation An, this is summation Bn, this is summation An plus Bn by definition. Okay, you see that some very basic BSc analysis also is very needed. That is why I keep saying, whatever you learn it thoroughly. If you learn it only from the point of view of exams, okay, your thing will be very, very patchy. You will never ever be confident and sure of what you are doing. Okay, I hope this was a little long session with, as usual, lot of interruptions. I hope you all enjoy. I hope so. Okay, let us meet again.